Hey there, 8th graders, and welcome to this explainer on scientific modeling. Today, we're going to explore exactly how we manage to wrap our heads around incredibly complex systems. It's kind of like a backstage pass to the tools scientists use literally every single day to decode the mysteries of our universe. So, let's get into it. Now, before we dive into the hard science, let's anchor our lesson right here. Proverbs chapter 3, verse 19 says, "By wisdom the Lord laid the earth's foundations." We're establishing this overarching theme of wisdom right out of the gate. Because as you'll see throughout this explainer, gathering facts is one thing, right? But using scientific tools correctly and actually understanding their boundaries, well, that requires a whole lot of wisdom. Okay, so here's our roadmap for today. First, understanding models. Second, why we use models. Third, the limits of models. Then, real-world examples, testing your knowledge. And finally, education rooted in morality. All right, part 1, understanding scientific models. I want you to imagine, just for a second, trying to study the entire solar system all at once, right there in your living room. Or, on the flip side, trying to hold and observe something as unbelievably tiny as a single human cell. We literally just can't do it without some help. And that is exactly where a scientific model comes in. It's a tool used by scientists to represent systems, processes, or objects that are just way too big, too small, too slow, or too fast to study directly. Models are basically the perfect solution to human limitations. They're these essential tools that help us step way beyond what our bare eyes can see, letting us make accurate predictions, explain really difficult concepts, and safely test out brand new ideas. Moving on to section 2, why we use models. When you look at the sheer practicality of models, the advantages are massive. I mean, they save us time, they save money, they conserve precious natural resources. But maybe most importantly, they physically keep us safe. Think about it. Engineers use a wind tunnel with a tiny scale model of an airplane to test aerodynamics way before they ever build a full-size jet. We avoid terrible disasters and save countless lives simply by testing out our biggest ideas on small, safe models first. Pretty amazing, right? Next up, Section 3, the limits of models. Now, here is the absolutely crucial caveat we have to understand. No model is perfect, not a single one. Models have serious limitations because, at the end of the day, they are just simplifications. They're not exact replicas of reality, and they deliberately leave out specific details to make studying easier. If we rely on them without understanding those limits, well, that can lead to completely false conclusions. For example, a climate model is amazing at predicting long-term global temperature trends, sure, but it can't predict exactly where one specific thunderstorm will hit next Tuesday. Or think about a cell diagram in your textbook. It brilliantly shows you the organelles, but it completely fails to show you their actual constant swirling movement inside a living cell. Because of those limitations, scientists have to be really smart about how they use them. When evaluating models, we walk step by step through 3 very specific questions. First, what does this model represent well? Second, what does it intentionally leave out? And third, how accurate is it compared to actual reality? Walking through these exact questions is how scientists judge when a model is truly appropriate to use and when it might just be leading us completely astray. All right, Section 4, real-world model examples. Let's look at some concrete examples to see exactly how this applies. Take the classic solar system model. On the advantage side, it's perfect for showing the order of the planets and their relative distances from the sun. But look at the limitation here. The actual distances and sizes are almost never to scale. A model is great for basic structure, but it might totally mislead us about the actual, massive, mind-boggling scale of outer space. Honestly, if it were truly to scale, the model wouldn't even fit inside your school building. We see a really similar dynamic with a food web diagram. The advantage here is fantastic. It clearly shows how energy flows between different organisms in an ecosystem, but the limitation? It completely misses the element of time. It doesn't show seasonal changes or animal migration patterns. So food webs are incredibly useful for general, big-picture relationships, but they are totally incomplete when it comes to capturing dynamic, time-based changes in nature. Finally, consider the plastic human heart model. The advantage is pretty obvious. It lets us study complex cardiac structure right at our desks without needing an actual dissection. However, the severe limitation is that a rigid plastic model cannot show the actual physical pumping of the heart, nor the complex electrical signals that actually make it beat. While this model is absolutely fantastic for anatomy lessons, actual physiological function has to be studied in completely different ways.
Okay, moving on to Section 5, testing your knowledge.
All right, We've covered a lot of ground, so it's time to actively reflect on what we've learned. Here are your first two homework prompts. Number 1, name one advantage of using a model in science. Number 2, name one limitation of a model you have personally used in class. I strongly encourage you to pause this explainer right now, grab a notebook, and formulate your own answers based on what you've learned. Active recall is how this knowledge truly sticks. Moving on to the final 3 prompts. Number 3, explain why models must be updated over time. Number 4, give an example of a model that saves time and resources. And number 5, describe one way a model could give misleading information. Continue challenging yourself to apply your knowledge of the what, why, and how of scientific modeling. If you can confidently answer these, you have officially mastered the science portion of our lesson. And that brings us to Section 6, Education Rooted in Morality. Let's tie everything we've learned today together into our overarching philosophy. We started this explainer by talking about wisdom, right? Our ultimate goal is intertwining biblical morality with education, which is really simply applying wisdom to our knowledge. Think about it. Just as a scientist needs profound wisdom to recognize a model's limits and avoid making dangerous false conclusions, a student needs a strong moral foundation to apply their education correctly and safely in the real world. Let's look at Romans chapter 8, verses 6 through 7, which promises peace of mind to everyone who keeps his or her mind spiritual. We share this scripture because this promise of peace isn't just, words on a page. It is the true lived experience of people who engage deeply with this content and deliberately pair their hard-earned knowledge with a spiritually grounded mind. Because here is the raw truth. Education without morality will hurt. Acquiring vast amounts of scientific knowledge without a moral compass to guide how you use it is not just an incomplete education. It's actively dangerous to yourself and to society. Knowledge without wisdom is exactly like a model without limits. It will eventually lead you astray. So I want to leave you with this provocative question to ponder long after this explainer ends. What is the point of being smart and supposedly educated if you're just going to continue making bad choices that hurt you and the people around you? True wisdom is knowing both how the complex world works and how to live gracefully within it. Think about how you'll choose to apply your new wisdom today. Thanks so much for joining me, and keep learning.